Of loss of circulation. So as we're drilling down, ideally what's happening is the mud's going down or air coming back up, and originally they were using lined pits in this area. But as we see, it comes in and some gets lost. Not all of it goes back up. Normally what happens is the wells that would be more likely impacted are the poorly constructed shallow wells, because they're vulnerable to this disturbance because they normally don't have enough casing to go down in the hole. So this was suggested. Penn State did a study and where they were trying to suggest some bromide spikes they saw in shallow wells might be associated with this. So some of the changes or suggestions that some of the companies were doing is going to closed loop drilling, putting all that back in tanks. Still not a regulatory requirement. One of the things companies have been doing is adding more strings. So instead of just one freshwater string, multiple strings to seal off to prevent that migration.
Can you explain what a string is?
A string would be a piece of steel casing that's cemented. So you start off drilling a larger diameter hole, put a piece of steel casing in. You go in and drill a smaller diameter hole, put another piece of steel casing in, cement grout, and work your way down.
So is string another word for casing?
Yes, steel casing. And so this is the example. This is a rock quarry over west of Dimmock, where you can actually see mud moving along those fracture zones or bedding planes in that formation. We're 80 feet down from the surface. So again, a lot of times when this becomes a problem, it's more of a problem for some of the older private wells that have very little casing, because they may only have 20, 30 feet of casing. And so up as you get closer and shallower, you have bedrock that's more fractured. Have more bedding plane fractures, and they're open, so you can have that mud loss. But again, you have to have seal more to the surface.
So you're saying what? The mud is actually migrating?
Yeah, in this case, this isn't actually mud. This is actually soil at a quarry, trying to show how that soil actually moved from the surface to 80 feet, just as water moves. So it's the same pathway that if you lose circulation you could follow. Just trying to give you a depiction of that.
I mean, like water, like a leaky roof, oh, my roof's leaking here. Well, it doesn't mean the hole's up there.
Right,
It might be back there.
Exactly.
But then water's going to find the little crack and seep out.
And the other issue with that is, the other issue is that when you have a loss of circulation, is what you might have isn't really stuff coming from the well itself.
Okay.
The well bore.
Okay, right.
So the well bore might lose to the formation. But when it loses to the formation, it creates a pressure wave.
It's pushing other things in the formation out.
Right. And so what happens at the well might not look like what's happening here, because what you're seeing is dirt that's around the well getting pushed in.
Okay.
So it might not have a signature of barium, strontium, or anything like that, or any mud.
Something else.
It would look like a natural issue, and the importance of maintaining a log, being vigilant about what's going on, in your area. So if you get your baseline testing done,
right,
and all of a sudden comes in and start doing a drilling or digging even in foundation work, all of a sudden the water gets dirty after a rain or during drilling.
right.
It could be that. But keeping that log is important.
Yeah.
Typically, when you have that, what you'll see is usually it's a short-term issue.
Okay.
You pump it well and that goes away.
Yeah.
And typically it'll be dirty water, iron, manganese, discolored water.
Okay.
Usually no methane signatures with that.
So back to
Anything
that
like that?
map where you said, oh, look at all these orange dots that aren't methane. Could be something like
And
this.
again, that's
It's something pushing
and-
something else now. Oh, look, this is in the water. How did
that
that
could
get
be
there?
it.
Well, that was in the rock next to you and it got pushed
right.
in.
And then part of that is that anecdotal. I mean, I think it's really critical to maintain a log.
Yeah.
Especially it's a part of being vigilant. What's going on in the area. So, for example, if something's going on and all of a sudden somebody just came in to build a pad, and they're taking away some of the surface soil, all of a sudden it rains and the water gets dirty, there could be a connection. We're taking off that soil layer, exposed rock. So again, maintaining that log is important that way, but having that baseline testing is critical. This would be about 2009. This is a video of methane gas migration at the well bore itself. For a Marcellus shale well. Again, this would be a well that had that single string of pipe, with cement, biggest issue was the use of that rather than multiple strings, especially in this area because there's shallow methane gas in the Catskill Formation that has lots of pressure.
Okay.
So if you don't have that extra string to seal it off, or you try to rely on one single string to seal it off, the gas coming out will actually create pathways for that. So that's been that biggest challenge they had from 2009 was that. And it was kind of lack of oversight from the, I'll say some of the, not so much the state, but from the professionals that gave them recommendations on how to construct in this area. Yeah.
And what about if there's methane migrating? What else can migrate with the methane into the surrounding area?
Yeah, usually when you have methane migration, the gas migration usually, it's kind of hard to move fluid with it, but what can actually happen is the methane can migrate, and when the methane migrates from, let's say, the deeper aquifer into the shallow aquifer, the methane can actually create a reduced zone in the aquifer. And when that happens, iron and manganese and other metals can get dissolved in the water, and that could also show up in the well. So you might see the water come out, have methane gas signature, and either come out clear, but then have higher levels of iron and manganese and maybe aluminum. Maybe sometimes arsenic. It's not really clear on the chemistry of arsenic if that'll happen. Or it'll come out methane dirty water. So I mean, that can happen, but it's usually that. Not so much a fluid movement that way. It usually doesn't carry much up along with it.
Any radioactivity can come up with it?
Well, with gas, it'll have radon. That can move along with it. If it does move, radon decays pretty quickly, unlike methane decomposes. So you might actually lose that. We do recommend radon as a part of a baseline test for the region as a whole, because it's a problem already. So we recommend doing that.
What about any other radioactivity? Do you recommend testing of any of the other radiums or uranium?
Yes. Yeah,
Do you recommend that?
What we do is on baseline testing, we kind of provided general recommendations into groupings. What are the more common problems and what are the least common problems? One of the things I found is a lot of homeowners felt very uncomfortable if you said you had to do all this, because they go, well, I can't afford all that, so I'm not going to do anything. So what we did is we created, I don't like calling it tiered approach, but created the approach that's kind of, these are the more likely common problems, these are less likely, and it does depend on where you're at and what's going on. So you really require to have that conversation. So if you're a shallow well, located right near where the natural gas drilling site is, and near the pad, then you should do more and provide that recommendation, like radium, 226, 223, 228, uranium. We do recommend radon.
And how many uraniums do you test for?
Well, at a minimum, we recommend the radium 226 and 228. Uranium, we'll recommend alpha and beta, even prior to that, because they're actually cheaper.
And
So
what about thorium? Do you?
Usually not, again, but you can. The way we recommend baseline testing to do, again, is always have the ability to add more. So for example, if one of the things we have from the citizen database, if we know we have a problem in that area, we'll recommend it. Or if you get your testing done and you have high levels of, let's say, alpha or beta, and you didn't do thorium, we'd recommend you add that onto that. So it's one of the challenges, because sometimes you don't know what to recommend until you see some of the data come back. That's one of the things we like.
Well, it makes sense chemically because of how things decompose and what you normally find together.
Yeah,
So.
and where you have that, again, is the wells that more likely have that issue are going to be your deeper wells that may have a saline water signature. So for example, your wells here that are deeper with a saline water signature are the ones that are more likely going to have slightly higher levels of alpha, beta, uranium, and radium. And
You mean the
uranium
wells here, meaning what's here?
here at Salt Springs State Park.
Salt Springs you're talking about.
Right. So some of the wells here that have that saline water signature, they're also going to have that signature that suggests high radioactivity, because that's what's in that saline water.
Now, do they have a baseline here at Salt Springs that you're familiar with?
I believe they do. I don't know. I've seen some of the data, but I believe you guys do have some baseline testing done.
Do you have a baseline for Salt Springs Park, for the water here?
I can,
Do you know anything about it?
I don't know.
Yeah.
I heard there is one, and is there a way of getting it?
That would be from them.
from the
Yeah,
board.
From,
Right.
or from
Right.
Deborah.
Right, 'cause-
Deborah would.
And then,
And the Park Service, I
and
guess.
then when you call a shallow well, what do you define as a shallow well?
Typically, a shallow well is going to be, it varies by region, typically 1 to 200 feet, maybe 300 at most.
So
But-
anything under 300 feet might be considered a shallow well?
Yes, but it does depend on place. So, you're also in a valley structure. So in a valley structure here, you might drill down only 200 feet, 300 feet, and hit saline water. So it is hard to,
Now, you know that the house here on Salt Springs, that they don't drink their water. They don't drink their water at both houses.
correct,
They're not potable, you understand that?
correct. Yeah,
And they
the
have a
saline water influence.
They have a filtration system,
Yes.
reverse osmosis in the rented house.
Yeah, I don't know what's that. I know that there's a water quality issue because they all have saline water signatures.
Right.
But you say you think that was here originally was?
Yes,
Yeah.
oh yeah.
This is the
Middle
original.
Mount.
Salt,
Yeah.
yeah. Middle
Yeah.
Salt.
Now, the thing is, if they had saline water signatures originally,
Yeah.
before we were concerned about water and before we had filtration systems, these homes are very old. They're
Sure.
from the 1800s,
Yeah.
right? Do you think that people drank the water? Up to what year did they actually drink the water? That's what I'd like to find
I
out.
don't know that. I mean, I would assume they did. Or, I mean, a lot of the older homes, I mean, I have friends that, they lived on cisterns. I mean, I have friends in the Poconos that are just 10 years older than me, and they have families of 4 that grew up collecting rainwater and stored it in the basement, and that's how they lived.
You know,
That-
I'm glad you brought that up because I went to a workshop on water down at Marywood, and that's one of the things they're going to suggest, like what they do in Bermuda.
Right.
They're going to suggest that for parts of the United
Right.
States
Yeah.
where you actually collect it. That would be, I think, phenomenally good.
And the other thing is, you really didn't get into having a drilled well until like the 50s and 60s. It was not very common to have a drilled well. All you might have had would be a dug well, and that dug well might be 20, 30 feet down. So, a dug well here might have fresh water completely because it's saline as you go deeper.
How deep do you think the saline might start? If it's 20 or 30 feet dug, they would have clear water, and they probably did that to have drinking water. How deep?
That wasn't something that was done. Brian was saying earlier that that's something we could do is profile for the depth.
Right.
In other words, you take your existing well and you keep profiling where
To
does
see
that
where
cup
the
spikes in.
where the
Yeah.
salinity starts. So
Yeah.
it could be at what, 100 feet maybe.
It could be 100, 200 feet.
Yeah.
And again, I
That's
think
not
the wells on
known,
the property are
but
like
it's probably something we
300 or
should do.
400.
So if they had a dug well, you mean the drilled wells are 300 feet?
Yes, I think that drilled wells are the newer ones that are drilled on
But a
the
dug
property.
well is usually 30 feet or less.
30, yeah, it's whatever you can hold open.
So that they might have done, and if they had springs, they might have drank from that.
Right, or the
There
surface
are
water
springs
runoff,
on the
because
property,
I
yeah.
think, and here they raised cattle, from what I remember from the history, looking
Yeah,
at the website. So again, they could have used surface water springs, runoff on the roof,
Probably.
collected it, and maybe had a dug well because of a drought. Didn't rely on drilling, because most drilling rigs really weren't available to the 50s and 60s,
Right.
unless you had a lot of money. And if
Right.
you did, you had the initial was a hammer rig, and not an air rotary rig. So, and even if you had a hammer rig, you only went down a couple 100 feet or so, because it took so long to drill.
Right.
And to be honest, a borehole here that produces saline water was done in the 1800s, and is 300 feet deep, and produces, that whatever 1 or 2 gallons of saline water come out of it with saturated level of methane. So it's very clear. If you go down 300 feet here,
Yeah.
we know we have saline water. We're in the saline aquifer because there it is, and that's what's coming out that borehole.
And then what kind of methane would you characterize at 300 feet?
Well, I don't know. I didn't do that. We didn't. I didn't do that test, but it is methane gas. I don't know if it's
So would you
biogenic.
you don't know if it's biogenic or
It'd
thermogenic?
be likely. My guess would be thermogenic.
You would consider
Well,
thermogenic?
I can't consider it. My guess is that it would be thermogenic just because of the rock formations that are here. There's not a lot of really biogenic might be more typical of, let's say, landfill gas, lake sediments, alluvial sediments. So we don't really have that here. So my guess would be more thermogenic gas.
So you don't think they have any biogenic gas here? How about the gas that's coming out of right on the surface of the ground? We have bubbling spring there. A bubbling,
That's the
what it's
300-foot
about.
borehole.
Yeah,
oh, that's the
borehole.
300-foot borehole
Yeah,
you're
that
talking
was
about?
drilled in the 1800s.
Oh, okay.
Yeah, it's like a square 4
Yeah,
inch
yeah.
in the water.
Yeah,
Yeah.
that was
And-
drilled around
See it.
300,
Oh, okay, and then-
18 something.
And then when you say thermogenic, would you also classify it as Marcellus thermogenic? Is there a classification, thermogenic and Marcellus?
Well, yeah, there is a way to differentiate between the various formations. That data has never been generated here that I know of.
But you're familiar with it?
Sure, yeah.
There is that kind of data somewhere for other areas?
I don't know about for other areas.
For other areas.
I think there was a study done up here where they actually did a signature for the gas here. I know I didn't do it, but I know that was published because they used it as a reference. One of the things where we're talking about drilling and how this might move, one of the issues is exactly that, what kind we talked about. First of all, drilling, we got to recreate those confining layers, those natural layers that were here before. So we don't get transmission or movement across a barrier that was impermeable or partially permeable. So that's one of the reasons why casing cement's critical. One of the things that's really critical, especially in places where you have the high pressure gas, not in the target formation, the Marcellus, but above it, if you have gas in that formation under high pressure, usually the weakest point of a cement job is the bottom. And where where the gas might migrate would be here. And what you might have a situation where when you go and look at effect, you go and measure that the gas coming out of the Marcellus and it has this signature. And I just did that by putting a blue dot. Well, you have this other gas that has another signature and I just put that as a red dot. What you might actually see is if you had a migration, you might not see any blue dots. The migration might be from this formation here. So you go look at it and go, hey, wait a second, we've had a migration, but we're not seeing gas from the Marcellus, we're seeing this gas here. That's still a methane gas migration. That's was a common problem up here back in 2009 before they changed. So one of the things is sealing off, when you get in those zones, putting extra cement and casing, sealing that off, having that extra barrier up near the surface rather than run deep private wells. So these deep private wells that are in saline water now become the next pathway. These become great locations that, if you're concerned about the hydrofracking have an effect on the pressure, these are places that you want to monitor. But these we can look at change over time and see if while there's pressure being applied down here, is that causing more salt water to come out? Is the pressure going to increase? Is the gas concentration changing? So these are great locations to actually monitor deep private wells.
Now, when you talk about pressure, what kind of pressure are you talking about? Is it hydrostatic pressure or what kind of pressure?
Well, I mean, if the concern is when you're hydrofracking, the pressure that's applied here.
Applied where? From the
In-
actual pressure that's being put down the borehole?
Yeah.
The borehole pressure.
Yeah, if there's a concern that the pressure that's used here.
And do you know what
in
the
high
pressures are? Have you heard about the pressures, what the PSI is?
Yeah, it depends on depth, but up in this area, it can be 9,000 to 10,000 psi. Here, so if you're worried about a migration this way of pressure, then one of the things you can monitor is while they're drilling, they can actually monitor that with microseismic techniques. And the other one for a homeowner or a group like you can actually monitor the water coming out of that borehole and the quality. If a pressure migration occurs, pressure moves instantaneously. So if you have a pressure wave migrating that causes a water level change here, you haven't had any movement of fluid from here yet. You just had pressure move. And so if they start hydrofracking, that water level goes up, and they stop and it goes down, that means the pressure moved in that, and so there's some connectivity, some connection. Did things move from here to here? Maybe not yet, but at least that's the easiest way to check and monitor. So again, these deep wells here that have the saline water signature, if you're going to keep them like this, they should be points of monitoring.
Now, how would you monitor it? What kind of equipment would you use?
You can monitor a couple ways. You can go to the borehole and extend the casing up so it doesn't flow out.
So you mean you would have to have a professional in here to actually raise your casing?
Yeah, that would be one way. I mean, that's in this situation.
And then when you raise the casing, then what do you do with it?
You could just measure the depth of water.
So how would you measure it? What kind of an apparatus would you use?
It depends. You can use a sonic water level sensor. You can measure with a line. You can do pressure transducers.
So you can do it inexpensively with a
Yeah.
line, or you could buy some kind of a what's the word?
You can use a pressure transducer. You can use sonic water level sensor. Measures the depth of water.
Sonic water level sensor. How expensive are those?
That's a little bit pricey. I mean, again, but a company could do that, or about $500. Or you can actually just measure it with you can make your own. All it is 2 electronic leads hooked to a battery. When you hit the water, you take those 2 electronic leads and hook them up to a battery and a light bulb. When they complete the circuit,
Right.
and
Then
so you
you
can
got
make
it
it for
done.
like $100 or less. So if you're handy. So I think that part of it is understanding which wells are most vulnerable to impact. And looking at the baseline data and saying, hey, from the baseline testing, how is that impact, how is my well vulnerable? And so if you're a shallow well, an older well with very little casing, a well in a pit, located maybe on the side of the slope on your way downhill, you're vulnerable typically from near surface activities. So going in and disturbing the site, drilling through the freshwater aquifer, that's when you're most vulnerable. Leaks, that's when you're most vulnerable. If you're a well that's deeper near the valley structure, you're probably more vulnerable to subsurface. All right? You're probably not methane gas migration, but a push. And so that's why you can do things like you're doing now, monitoring with meters, and let's keep an eye on that change. So I don't think they've started gas drilling in here in your lease section, right?
Oh, there's gas
Ours
drilling.
they have, yeah.
There's gas
Yours?
drilling.
Okay.
Not in
I wasn't
Johnson.
sure.
But there's gas drilling just like a quarter of a mile up. We have
Right.
several wells that have been with poor casings and spills.
Okay.
Major violations right on that site, the Depew site,
Okay.
which is within walking
What is
distance
that?
of within a half
Right.
a mile.
So those are the things that you could do, with the stuff you have.
Okay.
You track
Which
things.
which is what we were doing with the
The
Lamada,
White Creek, yeah.
the
Yeah.
Lamada meters.
Yeah, there were, like some kind of just monitoring what's happening, obviously doing the baseline testing, using the meters to see if there's a change. If the readings go up quite a bit. It's hard to say what quite a bit is.
Yeah, what is quite a
But
bit.
it depends what the initial one is.
Yeah.
So, and again, it's a guide. So, again, that's the idea. That you do it, and you see what's going on, and so you can look at change. So, if you're out there and your normal reading on the string was 100, and it goes up to, and it didn't rain, and nothing went on, and it goes up to 1,000 or 10,000, that's a change. That's a big change. If you're going from
Right.
100 to 110 or 120 or whatever you normally get,
That's it.
and so depends on place.
I mean, statistics, you can put your data
Yeah,
into just a statistics package, and so then you get your, your boundaries, and
Right.
your limits with
Right,
your
and I think
standard of
that's what-
deviation,
Right,
basically.
Alarm did
what-
that, which I
yeah.
think when they did the training, they give you guys as a spreadsheet that automatically calculates
Yeah,
for you what
Excel.
would be within one standard deviation or
Right,
two.
Excel will do that, for you.
Yep.
You can set up a spreadsheet
Yeah.
where you have all your data in, and then look at your standard deviation.
Are you still putting data on EL rows?
I haven't in a while.
I don't even see it on the site anymore.
Oh, really?
I didn't see it
Yeah.
when I
And
looked
then-
recently.
And then again, you want to look for example, if that well had signs of saline water or methane gas already. So I don't mean that the levels were already high,
Right.
but if you had, let's say, a barium in the well approaching the drinking barium standard, or you had methane 7 milligrams per liter above, again, that well is going to be probably more vulnerable from the bottom up. And, so again, you want to look for those
So
things
if your methane was lower in pre-test, let's say 1 milligram per liter,
Sure.
or under a milligram per liter, 0.5 milligrams, would you consider that a vulnerable well to
Probably
methane?
not. No, probably not. Typically, most of the wells in general have methane levels below 2. Definitely below 1.
Most of the wells where?
In Pennsylvania, northeast.
What about Susquehanna County? What's
Well,
the
again,
naturally before drilling, the most methane or the least methane that you've seen?
well, probably the least methane is not detectable. The most is actually saturated. That dates back to reports in the 30s.
So saturated means
Well, saturated at the surface means 28.
28
28 to 30 milligrams per liter. Sometimes you'll see, what'll happen is they'll do baseline testing and say the methane level's at 60. what actually happens is anytime a water well has a methane concentration over 28 or 30, when you're pulling water out of a well, the pump is down a couple hundred feet. The methane level in that water column is way more than the methane concentration at the surface because of the pressure. It can actually hold more methane. So for example, on the top of my head, I think about a 250-foot well that has a static water level of 50 feet. At the surface, this methane level will be 28 milligrams per liter. At 250 feet, it's about 200. So if you get a water sample out of a well that's above 28 and 30, it's actually super saturated with methane because it hasn't had the opportunity to outgas. Because you're pulling it from 200 feet down.
Yeah, okay.
So really any data above 28 and 30 is kind of meaningless because it's out of equilibrium. It's just super saturated.
Now, did you find that from pre-drill? Those are pre-drill tests that have no gas drilling nearby, and they had that kind of saturation?
No, you've seen, well, there's not a lot. I mean, back in the 30s, they talked about saturated levels of methane, what the values were. Some of that data is pre-drill data.
When you talk 30s, you're talking about from this area?
1930s, yeah.
From Susquehanna County. And,
Yeah.
and did they test, were they able to test, and they could tell you that it was milligrams per liter in the 30s?
Yeah. Oh, sure.
And they were able to test?
Yeah, that's in a USGS geological report. I have a copy of that.
And do you know what sections of our county had saturated levels?
In that report, it talks about the different town names and townships where they found it. And that report's on the website where you can download the whole thing.
On your website?
Yeah.
Oh, okay, so we could download that geological report?
Yeah, it actually includes the map too.
Cool.
We're able to find. So again, do we have other things? So usually the shallow wells will have, again, it's vulnerable from near activities. We'll have a bacterial problem. Not always have a problem with chloride or sodium. They may have intermittent discolored water naturally. It rains or recharges. Might be their problem. So these would be wells you'd be more concerned about near surface activities. And the other thing is, deeper wells, we might have a subsurface. And the issue is, when we have the testing done, we need to fix it. If you have a well that has a bacterial problem, the fix isn't putting a UV filter on. The fix is going in there and figuring out why the bacteria is short-circuiting.
Right.
And maybe extending the cement the casing, sealing that off, and recreating that barrier. Putting a UV system on doesn't fix that problem.
Can you get high bacteria because of gas drilling nearby? Can that affect people's wells?
I wouldn't probably say it would be the most typical.
But is it possible?
Any kind of a well that's vulnerable to surface water, near surface water influence, and you can have an activity doing foundation digging that it rains and you get runoff and it goes right in the rock. You can move bacteria easy that way. For streams and surface waters, they need these baseline testing done. Maybe not so detailed because it always changes. So it's more about getting some level of understanding of what's going on there, and then kind of just doing some screening to do exactly what you mentioned. Is getting that range of variables. The connectivity to water tends to be in this range. What's really more important is visual. Go and taking a look. Hey, there's no foam, there's no debris, there's not brown. Because not only do we have natural gas development up here, we have farming, road runoff, septic systems that all can have an adverse impact on stream quality.
And then what about doing visual if you see much more, let's say, algae growing? Could that be a change to be concerned about? If it's more of it than ever, earlier than ever, is that an indicator of anything, a clue?
Well, algae, typically an algae growth is a nutrient growth. I would probably say most of them that I've seen have been related to farming, ag runoff. Most of algae blooms are associated with phosphate moving through the environment. So most of phosphate is fertilizers, your manures. So you have lots of phosphate.
And what about sedimentation, increased sedimentation movement off?
Well, sedimentation would be, so erosion and runoff would be, so any kind of, going out there, and I think I mentioned discolored water, seeing that, that's where you'll get phosphate moving, so sediment getting into the stream. Always maintain a photographic record. That's actually more, to be honest, I think more than monitoring, the value of monitoring isn't so much the monitoring, it's a pair of eyes. something going on, saying, hey, this is how it normally looks and it doesn't look like that. Something's going on. Don't know what that something is, but something changed. And knowing when to call. Knowing when to call and when not to call. Kind of, what is this? And we got to be all forms of pollution are of an issue. Just like driving up in the rainstorm, you can see driveways. Some produce tons of sediment. Tons of dirt coming off that driveway. Then we have a gravel driveway that had compacted, was nice and clean. We had a paved driveway, lots of water, not a lot of sediment. So all of those play a role on making those changes, because that sediment can have lots of phosphate in it that causes algae blooms. So all those are changes we need to kind of make in lifestyle when we look at this issue, especially on non-point source pollutions. Again, you have some of the monitoring things you have here. You have these little inexpensive meters you guys use. I have some dip testers that I'll let you play with. Again, there's self-testing kits. Again, great for classes. There's online real-time stuff. This gets a little bit more expensive, but for a business or a place like this, you can actually have it and it collects the data in real time. They are testing a product now. I don't remember the name of it. I think it's called the Fish or something like that, where it's actually a little device that you can put in the toilet tank, and I think it measures connectivity. But it stores the data, and you can download it. I think one of the universities developed it, so they're testing it now. Or you can buy a slightly better upscale meter, and so I'm going to give you a couple of those, so you can use that along with your other probe. The one meter I had measures pH and connectivity simultaneously, and it's a longer probe, so you don't have to, really get right into the stream with it. A little safer. Where possible, you always want to measure connectivity. So if you have a choice and you're educating in terms of buying a meter, you'd want something that measures connectivity rather than TDS, or total dissolved solids, because in the field you can't measure TDS. That's actually a laboratory test. There are some meters out there that are called TDS meters, and what they actually do is they measure connectivity, and there's a fudge factor.
This does TDS
Yeah.
and salinity.
Right, and so what that does is, for that meter, what you do is you'll take a connectivity sample and a connectivity standard like you have, and that connectivity standard, they have a TDS value for the standard. But that TDS standard is only for a certain matrix, certain water matrix. So for a natural water matrix that doesn't have a lot of sodium in it, the relationship between TDS and connectivity is about 0.55 to 6. All right? So if I had a connectivity reading of 1, the TDS is 0.5 to 0.6. For salt water, that's not the ratio anymore. The ratio is 0.9. So if you had a reading of 1 connectivity, the actual TDS is 0.9. So I know when Oram was developing that program, we had a conversation about that, and we recommended not using TDS meters and doing connectivity meters. Because with connectivity, what you can do is, you can measure the connectivity, it's always the same, and then what you do is you do baseline, you do a sample for TDS, total dissolved solids, you take that to the lab and say, okay, I got a connectivity of 100, and I got a TDS of 50. I got a connectivity of 100, I got a TDS of 90. My ratio is 0.9. I went to the stream down gradient, where the saline water comes in, where they mix, and my ratio is 0.7. So with that, you can then, and so that's what I recommended to them, because that actually creates good value.
That's algebra.
Okay? Simple math, where you can put that right in the spreadsheet. And so that was one of the reasons I measured.
So are they willing to change over to conductivity only as opposed to TDS?
Well, again, that's my recommendation is, when I give the talk, is you buy those meters. And you can buy handheld meters that give you connectivity.
So
over
we can't
TDS.
just use those and just do the conductivity?
Well, they're designed, I have to look at those.
Yeah, you look at it and tell us what you
And then
think.
what you can do with those meters is, again, the way to, if that's the meter you have, what you can do is do what you can with it. What you can do with that meter is you can go measure the TDS,
Okay,
and then go take a sample, take it to the lab, and say this is the correction factor.
okay.
Or the other one is, if you have multiple connectivity meters, you have 2 or 3 of them, Then you go and say, this is the one for streams. And you go in there and program in the 0.5 ratio for freshwater streams. The other one that's saltwater, you program into it, the
I
0.9. So that's what so that was my second recommendation to them. If you already have TDS meters,
I see.
get
Program
them
it.
people to do TDS, check what the ratio should be, and program the
Program it
right
in.
value, and tell them only use this meter for this application. All right, because you don't want people to generate bad data,
Right.
raise a red flag, and be wrong. Because
Right.
we don't want to cry wolf, because then we start looking bad. We
Right.
want, when there's an issue, we want to document it, and that's why photographs are important.
But then
Yes.
can you program that?
Well, I have to see on that meter,
Yes,
but most of them you
Look,
can.
look.
Most of them you can?
Yeah.
The thing is, even if it's wrong or if it's off, if you see an increase, some kind of a significant increase, you're going to test anyway at some point, and then you can find
Absolutely.
out if there is any real problem.
Right, and that becomes a
Right.
difference, because if you go to that, if you go and compare that meter setup for the stream to over here, you kind of stream water, you're going to underestimate the TDS in salt water, right? All the time. You're going to always underestimate the worst case.
Yeah.
So
If you
that's
kn-
another reason why you'd want to, find out and set that up that way. So you never want to overestimate on your worst case. If you want to overestimate, you always want to overestimate on the least possible concern, right? I always want to overestimate on fresh water. I don't want to
Right.
underestimate my saltwater impacts. So again, another way of looking at it. The other thing I put up is just one of the things that in the area of, this is some data we worked with a lake community in Wayne County, looking at what problems they had. There's no gas drilling there at all, and what the percent occurrence for various things are. So we have no gas drilling in the area. Really, almost all the wells in this part of Wayne County have no methane signatures. Maybe in the northeast, in the northwest part of Wayne, there'd be more. But we have iron manganese problems, and then we're also seeing detects for barium, strontium, and sodium. So trying to get people to realize that some of this does occur naturally, that we do have some of this either coming out of the rocks themselves, or because we have a slight influence of saline water in that area. That's there. So trying to just make people aware of what those things are. We have another lake community we did. Again, in the same area. This was the percent occurrence this was more towards Pike County, of what we're seeing, that we have iron issues, lead, manganese, corrosive water. What is the lead? Sorry. Well, it's corrosive water, because half of the wells have really low pH, so it's actually leaching the metals out of the pipe. And at the same time, we saw some, high levels of bacteria, and that's typically associated with that poorly constructed wells, the older wells. There were a couple in pits where water was actually going right into the well. And then sodium issues, strontium, barium, and also, in this case, we didn't have a lot of arsenic above the drinking water standards. We had just some detects. If this was New Jersey, that would be above the drinking water standard. New Jersey's drinking water standard for arsenic is 0.005. Actually, in northern New Jersey, about a third of the private wells in northern New Jersey have arsenic above the drinking water standard, because their standard is 0.005. Our standard in PA is 0.010. So I think this is part important, especially when you're educating the homeowner, they're getting results back. A lot of homeowners don't know what's in the water to start with pre-drilling. They don't expect to have chloride and sulfate at all, but they don't know it's there. And it's important to educate on what the drinking water standard is and what it means. So that's one of the things that's critical.
Now, what can you do about high arsenic that's above the standard?
High arsenic, most of the time, the first thing you want to check is if you have an iron problem. So if you have an arsenic problem and iron problem simultaneously, typically if you treat the iron, you'll take out the arsenic simultaneously, because the arsenic will actually, as the iron becomes oxidized or transformed, it'll actually go into the matrix of that particle that's created. So it'll be taken out simultaneously.
And then how do you get rid of the iron? What do you do with iron?
Well, iron could be water softeners. Iron could be oxidizing filters and filter them out as particles. There's a couple different technologies. Ozone will work for iron, ozone will work for manganese, water softeners work for iron, manganese. Arsenic, if that doesn't work for arsenic, there's actually activated material that scavenger the arsenic out.
Have you seen the $38,000 filtering systems that Cabot put in Dimick for several homes? Have you ever looked at them and see what you think of them?
I've been to a few of the houses that have ozonation systems in.
What about the ones that are in separate sheds? They have,
Yes, yeah.
they have separate sheds for them?
Yeah.
And
Yeah,
what do you think of those systems? Have you
Well, the ones I've seen, the post and pre, the ones I've seen the data on, they seem to work fairly well.
Are
I
the-
know the one homeowner, we've been up there several times with them when they got the results back, and we review it for them.
And are they drinking the water after the changes? Do you know if they're drinking?
That person is, yes. Yeah.
And-
I know when they were getting water hauled to them, they were, they had this thing because it had some chlorine residual and they weren't used to it. So that was a concern. But to my understanding, they're using and drinking that water from that one I've been to.
And have you been to any where they're not drinking the water and they have the filtration system?
I've been offered to go there to people's houses and not say where I was, but.
They wouldn't let you in?
No. I made that available, that I go up there for free and keep everything confidential.
And what would you do if you went for free? What would you?
Well, again, the person would, if they asked me, that they had a question or didn't know what was going on, or just like if somebody has data they don't understand, again, look at it for them and say, yeah, you need to ask these people to test for this, this, and this. And we've done that. And especially in Western PA, people got their baseline testing back, wrote a letter saying, hey, you missed testing for these 4 things. In this sample, based on what's there, you should be testing for radionuclides. Wrote a letter, signed it, and handed it over to the gas company and said, same thing with, we had one person that did a shale test. They got the data back from shale test, and I looked at the data for them and said, this data suggests you should have checked for this and this. Either ask shale test to do that for you, or go and test for these things yourself. So that's kind of what we were trying to do.
Recommendation,
Yeah.
basically, of like.
Now, the thing is, you're recommending, but Moody Consulting is testing for Cabot every single week, those systems.
Okay.
So you would think that they are covering all the parameters, or they may not be. Have you seen any of the Moody results that are being tested every single week in Dimick?
Again, for the homeowners that send me that, yeah.
So you have seen some of those?
Yes.
And then have you seen any deficiencies in that kind of testing?
In that, no. And what we've seen from the ones that showed them to me, no.
No?
Yeah, that way. So again, the concept is trying to work together, and getting the people, and getting their baseline water testing, sharing the data, just having a conversation. Because one issue that could come up is my water's fine, but I've worked on cases in Monroe County where my water's fine, but the guy's water on the hill is a problem. For example, I had one case in Monroe County, Hamilton Township, where about 35 homeowners walked into the township and said, hey, we all have bacteria in our water, how'd it get here? And, come to find out, the guy up on the hill, he had a problem with his well, with bacteria. So rather than fixing the casing, they put a treatment system in. And a couple of years later, that problem worked its way down all these people. So having that conversation is important. We don't have a really good way of fixing private wells yet. That would be a wonderful program for Pennsylvania, because I think it's not the people's fault if their well is poorly constructed. And have a bacterial issue. These are conduits into our aquifer that we need to fix. Again, in places where we have local water authorities, working with them, because they have a vested interest, because they're typically downgrading of private wells. So whatever gets in the private well works its way down to them. So there are things like source water protection plans, where you can work with water authorities to develop that types of programs. Again, fixing private wells. Again, we're encouraging baseline testing and definitely getting our surface waters tested. Critical. Tracking change. One is, it's not the perfect frac focus. I wish frac focus would put concentrations, not just percent use. That has been my recommendation. The citizen database, we have that. We don't ever generate a map that shows you where all the data points are because of confidentiality with the people, but we try to integrate that. A nice site is Frac Tracker. I like those guys, and I provide some recommendations for them where people can tell their stories about what problems they run into, how they dealt with that industry, positive and negative. Mostly, again, positive and negative. If they were able to work out their problems or not. But it's a great place to see what happens have occurred. Again, the citizen database has worked out real well. We've helped, the people we helped in DIMIC, at least getting them, explaining the results to them, what they should be concerned about, other data, what kind of testing, they really needed to get done. I was actually out there in some of the private wells during the EPA sampling of those for those homeowners. Really working together, track change, kind of what you're doing. Getting kids in, monitoring those samples are perfect. Things of that nature are critical, and being that bridge between both things, especially here where you guys have been managing that for a long time. And that's kind of what I had that way. So if you want to go over the check, I can leave this stuff here, and let me save that. And then we can, take the LEL meter with me, and I'll grab one of the water quality
Okay, I'll get
meters.
my camera there,
Yeah.
or my video, so we can actually hear what
Sure.
he's saying, so we
Okay.
can review.
Sure, that sounds good. Is that in the car?
Yeah, I always had it with me.
Yeah, since I'm holding the program here at the park, I have to always do the old sign-in sheet. And this is yours, right?
That's all my stuff, yeah.
One of the things you always want to do is when you come out to a site, do a photo documentation, and you're going to kind of gauge the clarity, what's going on. So you have that staff gauge you want to put up. Probably the best thing is to put it up in a place that's always wet. So maybe you can go to like Ben Meadows and pick up an actual staff gauge and mount it to that wall over there. Okay. And so when you want to see how high the water is, it's always mounted at that one point for you. So you don't have to keep, wading in. Usually it is better to wade into the stream to collect, but we're not really prepared for that. I know I'm not.
And it's usually not as high, obviously.
So it's usually, you want to come back to the same place to do your sampling. And one of the things you don't want to do are things like this, right? You don't want to do that, okay?
And why don't you? What would you say?
Well, you don't want to like measure water quality while you're upstream disturbing things. So typically you try to get to a place where you can be off to the side, which is one of the reasons why these kind of meters are nice, is that I can actually take it and I can actually put it in upstream. That's where I'm at. And this one, it does pH.
Okay.
So right now the pH of the stream is 7.6. I can then read connectivity by just hitting a button. I already calibrated it. It has a connectivity of 70 microsiemens. That's very low. That's fresh water.
And that's after a rainstorm, because then we
Yeah.
have a rainstorm. What does a rainstorm do to conductivity?
It can do two things. One, it can dilute. And the other thing too is the rainstorm could cause clay to move. Clay is a charged particle, and clays can increase the conductivity of water. So it can go either one.
It can increase it or decrease it?
Yes.
Either one. And how much does a meter like that cost?
This is probably about $175. Yeah, I prefer them than.
Oh, that
the
seems
ones-
nice, yeah, because it's about double the price of this.
Right. And what's nice about it is you can just when the probe finally goes, which might be 2 years or 3 years, you can just buy a replacement probe.
Where did you buy that?
Yeah, where do you find it?
Oh,
Yeah.
this is by Hanna.
Hannah?
Hanna, Hanna Instruments.
Okay, and
Yeah.
then,
And the calibration is really easy. You
Is
just have
it?
a little standard. There's a knob right here. When you want to do pH, you put it in a 7 standard and just go to pH scale, turn the knob, rinse it off, go to connectivity, turn the knob. That's a pain. Those probes are.
What is it called again?
This is a Hanna meter. I'll email you the
Hanna,
model
okay.
number and all that. That way.
yeah, and
If
then
you need it, just
how
give me your
often do
email.
you have to calibrate?
I typically, if you're doing certified work, daily. If you're doing like a monthly screening, just, basically when you go out that month to sample, that's all you really need to do. You want to rinse it off when you're done with fresh water. So I like these. One of the nice things about these kind of things, you can do like surveys. So like for example, you have a stream where, like you have over here, we have a tributary coming in. If you go right where the tributary comes in, those two waters aren't mixed. So you can actually just go right across the stream and see if the water quality is the same. And if it's not, say, okay, we got to go further downstream because that's when it's finally mixed. So, and again, it's a little bit more convenient, especially getting to the side or when this is really roaring. When this is really high, you can't really get here. You might have to be over here. Gives you that flexibility. So I prefer those.
And then what do you test for? How many elements?
Well, this one here is pH, connectivity. You can put the fudge factor in for TDS and get a value for that.
So that would be 35.
That would, yes, I would,
Correct.
right. So I see how this one's calibrated. Yeah, that would be okay for you. I have it calibrated for salt.
Oh.
So this is this meter is my higher meter for like salt reading.
Now, do you consider this a saline source?
No, but, so what I did was I have this calibrated as if it was a salt source. So when I did that TDS, I got a different number than she said 35, and I got 63. So that's why I said 35.
You know, I've done the TDS for the house, and it's so high. Have you
Yes.
ever tested TDS for the house? You can see that difference.
Yeah. No, the wells are saline water influence.
Right, I know.
Units of measurement for the conductivity,
Micro Siemens, so it's U, S,
Siemens.
then a division line,
Okay.
centimeters, SCM, micro Siemens per centimeter. So basically, it's the ability to carry a charge. Micro Siemens is reverse resistance, inverse resistance, and then centimeters for distance. So basically in here, there's two electrodes so far apart, so you're measuring the resistance across those two electrodes. That's what the value means. What's nice again,
It's been a long time since physics.
oh, that's fine.
Siemens.
One of the things you might want to get yourself because of what you work is you can buy sampling cups. They're not that expensive. Basically, it's like a long arm with a cup on it. So if you want to, always sample mid-water, it's 12 foot long. Go there and get your sample, bring it out, so you don't have to wade in.
Yeah.
Again, if you guys doing yourself. What these are nice is like gift stuff. You can actually just. Dip them in the water. The way they react. Yep. So you dip that in the water and do a color code. So the top one is for nitrate. So you work your way across and say, hey, the value is between 2 and 5. No, not a great. That's something great. But typically, if this was a water well, you would want to say, hey, this is a water sample we should take to the lab. This is very typical after a rain event for a stream. If you came here during like normal flow, your nitrate levels will be down here.
Okay.
It also tests for nitrite, the reduced form, and that's very low. Nitrite is the one that's more toxic between the both of them. So
You
this
should have
is
a zoom on that camera. Can you know how to do a zoom?
Yeah.
okay.
And you don't have to go right on top of it.
I'll back
Am I
off.
blocking you?
No, that's okay. Yeah, it's blocking,
Yeah.
but then you don't have to really be inside. You see the zoom? You can see really well. They have good zooms on those
Yeah.
usually.
So this is again nice for kids.
Yeah.
And a good screening test. So again, as I mentioned before, if you're going to do some more homeowner type programs or bring them in, or get more people to come to programs, offer like a free water screening test and say, have this laying around, let them dip their water sample, take a look. Like I said, if the level's above 5, usually we'll recommend for them to get their nitrate tested. If it's above 10, that's a drinking water issue. Would be a drinking water issue, primarily if they have infants. Really little kids, because it's called blue baby syndrome. They can get exposed to. For nitrite, NO2, the one down here, the drinking water standard is 1. So if you're above 1, it's an issue. So that's a really nice, real inexpensive thing. Does really nice work to educate the community. Also, if you're doing a stream assessment and you're looking for an erosion problem, a nutrient problem, you can go and do nothing, big number, high conductivity, this is the place to do sampling. So if you're trying to develop a sampling plan, this would be really nice and helpful.
So what is it called? What's on that label on that?
This tests for nitrate.
And what's on the, turn the label like
Oh,
this.
here you go.
It's called a nitrate, nitrite,
And this is
aqua check.
Aqua Check. This is available from Hawk Company. I think this is 20
Hawk? How do you spell Hawk?
HACH.
H-A-C-H.
Yeah, I think it's about $25. I mean, 25 tests, and I think it's only about $15.
15?
Yep. Hawk Company, same thing. Sells another product. I like this. It's a 5-in-1 test kit. It has, you can do chlorine residual, alkalinity, hardness on it, and pH. We use this a lot, especially when we have homeowners that have shock disinfected the well. We want to make sure it was purged enough before they take a bacterial sample. So for homeowners doing shock well dissections because they have bacteria, I'll say purge the well, check the chlorine level, make sure it's not detectable, and then we'll run that sample. So what alkalinity is for a stream, alkalinity actually creates the buffering capacity. So when we have a rain event, that acid deposition, you know, we acid rain, it's the alkalinity of the stream, the carbonate in the stream that prevents the pH from changing. Sudden pH changes are really something that causes impact in juvenile fish more than anything else. Sometimes eggs, but mostly juvenile, the fry, are very vulnerable to sudden changes in alkalinity. Hardness. Hardness is typical. Most hardness around here tends to be low, but they do have some interbedded calcareous material. So what sometimes we do to manage alkalinity waters is add carbonate. So like the rip wrapping, if you ever put rip wrapping in here to stabilize this, you would go with like a dolomite or a limestone, because it'll add buffering capacity, help stabilize this because it's eroding. And then pH is, if you can't afford a pH meter, you know, you want to know if you're in a good range. All right? And so all that's in one quick test. I think on this bottle you get 50 of them, and I think they run about $20. So again, nice, quick. If you're having an education program from homeowners, hey, come in and get a free water screen. It costs you like nothing to get them to come to an event, to come out to your event, and you're giving them some value.
So you're calibrating.
Right. So we took it off, we rinsed it, we put it in it, we rinsed it off, we put it in a calibration solution. We had to change the mode to read conductivity. That's right at the bottom. It would come up conductivity, C-O-N-D. So we knew we're in conductivity. Once we put it in we got it in conductivity. We then hit the cal button, and it automatically goes through a calibration. It assumes you're using that standard. 1430. That's what it assumes you're using. If you do this and grab a 760 or a 14,000, it doesn't know that. It assumes it's 1413. So you have to always use the right standard with this. And then this is basically a salt solution. So that's something you could just, I would never throw it in the stream. I'd go away from the stream and put it over there.
You can't reuse it and put it back in the
No,
box?
no. You never want to reuse standard.
You run the risk of contaminating the standard, and then everything else is, whether or not that happens, you know, but still, then you're faulting all your data on a standard.
This is the second reason I hate this meter. I am a fat guy. Okay? If you take the meter and hang it and look like that, you can't read anything, right? Which is why they give you these things. They read from the side. So the only way to really use it, which is one of the reasons I don't like it, is you have to really kind of get in.
Don't
Yeah, but
fall in.
we have sample bottles they gave us.
Well, I get
Sample container.
Yeah, they have. I don't have one there.
Yeah, I have it with me. I just left it over there. Forgot.
So with this, I'm getting a reading of a 58.
For conductivity?
I said 700.
Before it was 70, now it's 58? It was 70.
78.
What do you say, 78?
78.
Okay, so it's close.
78.1.
And you said 70, I think, with the other one, so
Yes.
it's close, right?
So again, that's why I think a sampling cup would work. Having more cups like that, they can put the sample in.
Right.
If you're going to reuse this for your sampling cup, you'd want to dump it, and then you want to rinse it 3 times.
With the water that you're sampling.
Yep, and when you rinse it 3 times, it's better to rinse a cup like this by filling it up halfway, mixing it, dumping it out. Let's say we wanted to rinse this. We dump this out. We go get some of the stream sample, put it in here, shake it up, dump it, shake it up, dump 3 times.
Okay.
It's better than filling up halfway and doing that than filling it up all the way 3 times.
And why is the difference?
Believe it or not, you actually get better removal of the previous sample by filling it up part way and shaking than just filling it up. That's like when I taught Wilkes at Wilkes, the first lab lesson is how to clean glassware.
Yeah, I remember doing that too. You swirl.
Yeah.
You swirl around the outside. I guess
swirl
the
and mix it.
motion
So-
allows things stuck to the
Yeah,
side.
and so those are the big issues. But I think again, sampling arm really good. Getting more cups would also be good for it. And so we could go and check out the salt spring.
Okay.
I have my LEL meter, so we can see if we actually get a reading for gas.
Oh yeah,
not.
good, that'd be nice.
So here's that.
Thank you. This is very helpful. You don't
Oh, sure.
know. It's very helpful.
Pipe, and remember I showed you the graph
Yeah.
where more methane might come out. You do that. Now again, that's what you'll
I
do.
heard more methane comes out when it's hot water.
Hot, yeah, so you can do cold and hot. More methane what happens is not more methane comes out, it comes out quicker.
Quicker.
Okay, because solubility changes. So when we heat the water up, it can't hold as much gas. So the solubility changes because it comes out quicker. Usually methane will come out of a fluid, water, in about under 2 minutes. So if you have a gas that's still outgassing after 2 minutes, it's not methane. Or it's not, there's something else other than methane in there. So if you have a gas that takes a while to come out, it's probably not methane.
What could it be then?
Oh, carbon dioxide, the big one. It's not radon. Radon, if it was that much radon, you're dead.
And you just wasted $1,000 on your meter.
Yeah, if it was that much radon to create that much effervescence, you'd die. Because it would be an asphyxiant.
Is there a uranium that is weapons grade that can be found in our water?
No. Not the concentration, no. It's not that high.
Because they tested in Dimick for weapons grade. Do you know which one is weapons grade uranium, the number? Was
Well-
it 220 something?
Well, 220, I think, uranium can be used for, 238.
238?
Yeah, so when you test for uranium, the issue would be, back in the 70s, in Pennsylvania, they assessed the Marcellus shale
You want to see us water test the
to look to
methane in
see
the well?
if there was enough uranium in there to be a fuel source.
What is it? We're going to test
And
the
that's
methane
where,
for
if you look at some of the wells that were drilled in the maps, and you see like some old wells drilled in the 70s.
You mean water wells?
No, actually wells down into the Marcellus.
Oh.
They cored it to see if there was enough uranium to actually use it to mine, and they found out there wasn't.
Now,
So-
which one is the weapons grade uranium? What
It could be
number?
probably 238.
238. But
Yeah.
have you seen any tests? I've seen tests where they actually have that on the list.
Yeah, well, it could be.
238.
It could be uranium 238, the parameter. It's just not high enough to be weapons grade.
But if they detect some of it, if there is a detection of it,
Yeah,
then
no, it
you
would-
still wouldn't call it weapons
No,
grade?
no, because weapons grade uranium is the concentration of it, having enough. Now, there's uranium in the formation. There's radium 226 and 228. That's the daughters, the breakdown. But it's not. You don't have really, really high concentration of it to be weapons to make weapons out of it, to purify it and get it to a weapon.
I also heard that Halliburton is using some weapons grade uranium in their testing probes. Do you know anything about that?
Yeah. Oh, actually, like
Down there.
geophysical equipment has radioisotopes in them. To be honest, that's how they, when they drill the Marcellus,
Yeah.
one of the things they look for is potassium signature, and so you know you're in productive
Right.
Marcellus shale because you're getting a potassium signature, or radioactive potassium. If you don't have radioactive potassium, you're not in the productive portion of the shale.
So if they're using some weapons grade uranium in the Halliburton equipment, do you think any of that might be getting into the water?
No, that's
Water wells?
That's self-contained
Oh, yeah, I see that.
geophysical equipment.
See the
You
bubbles?
want to come on this side so you can see?
What?
Sure.
What? Oh, yes.
You want to come over?
Yes, I'll come
mine,
over that
so then
way.
you
Oh,
can
yeah.
see him facing towards us.
So here's the bubbles right in the middle there.
Just thought you'd be able to see.
And this is, do you know how deep that 300 feet it was drilled, and it's encased in metal?
I believe it's down 3. I don't know how far the casing was down. It was done around the 1850s, I think,
Oh,
and that was in the presentation. So we're just right here at the surface. We're only getting like maybe 1% LEL, so we're not getting a lot. But that is, you can actually light this.
Okay.
It's on the video.
Now, if it's 1%, what would that be in milligrams per liter? How would you?
Let's see if it goes up a little bit more. We're getting some more. 15. There we go. Nice.
Wow.
It's always tough to know that. My guess would be in this. Well, I know it's super saturated in the solution. In this solution here, it's 28 to 30.
28 to 30 milligrams, you
In
figure?
the water, yeah, it's fully saturated.
Of methane.
Methane.
Of methane.
So you're saying that one can be lit,
Yeah,
probably?
we can actually light the.
Too bad we don't have a lighter. I have like a barbecue lighter in my car.
Yeah.
that would
It's up to
like-
them.
That
Got
would
little
work.
kids around. I don't want to encourage them to do it, but yeah,
Well,
you
no,
can
we
do
don't.
it.
Yeah,
we don't have any little kids around.
Yeah.
I saw that on TV where someone took a lighter and
Yeah.
they were,
Yeah. Yeah. The
And they did it
video.
on this thing or something else?
well, they said
Well, they
it
have
was
done
in
it from the
a little
faucet.
Snake Creek, so I don't know if it
Oh,
was there.
Snake Creek.
Yeah.
This
The.
is Salt Creek,
Snake
right?
Creek.
Oh, yeah,
Salt
that's
Creek.
different. Yeah, that
Yeah,
was
we do have
Snake
that.
Creek.
We-
That's
we-
further up, about a
And
mile.
I'll give you the link to the YouTube video
Okay.
that we have for this.
And what does it show in the YouTube video?
That actually lighting it.
Lighting it?
Yeah. That was done in 2010.
Now, when they can light the faucets on fire, do you know how many milligrams there might be in the water at that point when they're lighting? If you're able to light your faucet on fire,
Yeah, typically what you're lighting is the gas that's coming out with the water. And again, that's typically 28 to 30 milligrams per
so it
liter
would
of
have to
water.
be 28 to 30 to light.
Yeah, it's super saturated.
So what are you getting here?
So the pH is going to take a while to go down. For now, over at the stream,
Yeah.
we had a conductivity of 70.
Yeah.
Okay, the conductivity here is 6,620.
Wow.
What does connectivity mean?
Conductivity is the ability of the water to carry a charge.
Oh,
The more stuff dissolved in the water, the higher the conductivity.
ability to charge.
Right, and then, but it's not always the same. So if I put sodium chloride in, you'll get one reading. If I take sodium chloride and let's say baking soda
Yeah.
and make it the same concentration, right? Same
Yeah.
amount in the water, I'll get different conductivities because the sodium chloride is more efficient
Yeah.
at the conductivity and moving conductivity.
Does that make a difference? Does the sodium content, is that
Yeah.
sodium chloride in this salt spring?
Yes. Yes.
Okay,
Sodium-
so that makes it more conductive.
Yes.
Yes.
Yes, there's also
With
some
the methane.
calcium and magnesium in here.
Okay.
But there's a lot of sodium.
Okay,
Yeah. And not a lot of alkalinity.
yeah,
It's a lot of salt, very little carbonate. So we have lots of carbonate over there.
okay.
But we have sodium, calcium, magnesium, very little carbonate, like baking soda, the
Right.
carbonate. If we had lots of carbonate, what we'd actually do is if we added baking soda, to
It
this, would precipitate out the calcium and
Oh,
magnesium.
okay, okay.
Yeah.
Now,
So we
would
have
you?
an estimated
Yeah.
TDS is above my meter, so it's over 1,000 milligrams per liter.
Well. Now, would you be able to drink that and not get sick, or what do you
No,
think?
no, this would make you sick.
Why would it make us sick?
Here,
I
you would.
know that.
The
I was
first
trying
thing
to
is that
think,
you're
okay.
way over the barium, so long term you have barium
but we
poisoning.
said I
Also,
tested
the taste of the water is you would actually taste the salt on here. So you have high levels of barium. So
And what's the salinity? Did you test the salinity on that?
well,
meter?
conductivity? Yeah, you basically get that.
Indirectly, yeah.
That would
indirectly.
correlate.
Because we have a salinity thing on our meter. It
I'll
tests
give you a rough
salinity.
percentage.
Yeah, we
pH
do.
is about 7.8.
So pH is not much difference.
Nope, no lot of difference in that. But the conductivity is extremely high.
Now, how do you know the barium is high?
Well, we have sampled this.
from past.
From the past, and the
Yep.
barium was high, so
Barium
then
high,
you would get
that's it.
sick from the barium.
Barium would make you sick in here. Now, they're also, this doesn't have a lot of sulfate in it, so it wouldn't be a diuretic. The sodium, though, is really high. That would be a diuretic. The calcium, magnesium, again, that would just cause a taste. The iron and manganese, very high. You'd have not only salty taste, but you would actually have a metallic taste. And there's also some aluminum in this.
Now, which part gives you the metallic taste? Because I've tasted metal sometimes.
Typically, iron and manganese are metallic taste to the water. Then you'd have the salt. The salt is the prominent one. Yes.
Is there a lot of iron in this water?
Yes, this was high in iron.
Does
You can
that
tell
go along? Does that correlate with the sodium?
if you
or
come over
not?
here. You can actually see it's starting to oxidize
Oh
down.
yeah,
See how
I
it
see
gets
it.
red?
I see it.
And so what's happening is the water's anaerobic.
Yeah.
Comes out of the anaerobic as it hits the oxygen from the air.
Ferrous oxide.
Yep, we actually get a change, and we start getting that iron precipitate out, so we can start seeing it.
So you're
that'll be-
starting to see like a reddish,
Yeah, reddish.
orange,
Yep.
orange, red.
And then further down, you may see a black. So what happens first is the iron oxidizes first,
Oh yeah.
quicker, and then manganese takes a lot longer. It stays in solution longer. And then one of the things you might see that was mentioned is sometimes you'll see a sheen, like a sheen
an
at the
oil
surface.
sheen.
And typically what that is a bacteria, here in this case.
Okay.
Now if you're in western PA
Yeah.
and saw a sheen, it actually could be oil.
It could be oil, because they
Yeah.
do oil drilling there.
Yeah, well, they have, and it's been seeping out of the ground since, I don't know, 1500s. And there are some of the old abandoned wells, actually, you'll have an oil sheen,
Yeah.
and you'll actually see wax.
Isn't that where Rockefeller built his first oil well?
I believe so. I thought it was there.
Yeah, it was a different name, though, who did the first well. I can't remember his name, I apologize.
But that was in
Titusville. Titusville was the first drilled well. Prior to the drilling well, what they were doing is they were capturing oil it would come out of the surface, and they would dig ponds and put berms up and catch the oil.
To capture it?
Yeah, and the Native Americans, they were using that too, because they were also using it as a skincare product and some other things. They'd catch them that way. But I can't remember, they got Drake. Drake was the first drilled well.
Yeah.
Yeah, and I don't know where he got his funding from. So
Maybe that's where
maybe got
Rockefeller-
Rockefeller.
Well, Rockefeller ended up
So-
being a primary
Yeah, and
exploiter
Yeah.
of that.
yeah. Yeah.
How deep did you say? I'm
This
sorry.
was done. The history that we were able to find. It said it was 300 feet down.
Okay.
This hole.
Yeah, get back
What they 300 feet down. What they wanted to do here back in the 1800s was the value of salt springs was the salt. We didn't have refrigeration,
Right.
so we needed a way to preserve foods, and salting was the way to do it. So what they wanted to do was to have a commercial operation where the methane was used
Okay.
to heat up the water to basically
To dry the-
evaporate and create salt, to send the salt to market.
And
What
I-
happened was, go
I
ahead.
was going to say, and I told the kids recently, I said, unfortunately, they didn't realize they could have been distilling it and selling spring water at the same time.
Yeah,
just
right,
by,
that's true.
Just by distilling off what they were boiling off.
Yeah. And what happened was they never got a whole lot of water out of the hole.
Oh.
And
Didn't have the pressure.
Right. And that's typical. Most of the saline water formations are not really permeable. They might have cracks in them, but they're not well connected. So what happens is there's solid rock masses with a crack, and it follows that plane of weakness. They drilled on it, and it's just not well connected. Whereas if we looked up here in the freshwater aquifer,
Yeah.
see all the bedding planes where the rock comes together in joints.
Yeah.
So the water in shallow in the freshwater aquifer is really well connected.
Okay.
And you can produce a lot of water because that joint migrates 300 feet, 500 feet in that direction. So if you can
get a lot
get
of
to it.
seepage, yeah.
And the other thing is he didn't have a pump. He couldn't pump the water
So
out.
they're looking for natural.
So he was looking for, because he was
Natural pressure?
natural pressure. So he didn't have the pump. So maybe you could actually, if you had a little pump, you could pump this at 10, 20 gallon a minute.
Yeah.
But he was relying on natural pressure to bring it out.
Yeah.
The formation rather than being able to pump it out, because they really didn't have that then.
Yeah.
To really pump, have any quantity to pump it out. Because then all of a sudden he needed more of a fuel source that he didn't have.
How's the drinking water for the people that are in this area?
Well,
They
Do
can't
they have
drink.
any evidence of that?
They can't drink on this property. Nobody's drinking their water. It's not potable. They have to have bottled water or reverse osmosis treatment in the house
Okay,
there.
but I mean, years ago, the
That's what I
farmers that
asked
were
him.
here-
I was wondering.
I don't know about the history. What I would guess
Yeah,
is
what they
the
did.
history. I mean, prior to probably about 1950s or 60s, there wasn't a lot of drilled wells. People relied on surface water streams,
Yeah.
and obviously we said the reading over there was 70. You know, nice and low. That's something you drink.
So the creek is good.
Yeah.
Okay, so they could drink
And so they could have done something like the creek. Maybe they had a pond on the property, use that. Could have collected water.
Or shallow well. You could have a dug well that's shallow. That's
Yeah.
Or
30 feet or less. So
Okay.
you're not in
Yeah.
that saline
Down
part.
there, okay.
and they just recently found an old hand dug well, just at the what's that?
Just at the carriage barn.
Carriage barn.
Oh, yeah?
Right in the porch. There's an old hand dug well. They just found.
And was it in
Still
good?
there?
Was it in good
They
shape?
just found it. They just found it and cleaned it out. There's a video of it.
Yeah, wow.
They found a dead bat in it.
Maybe you drink the water.
Right.
I don't know.
Is that right? Is
But,
it on
where are you guys
YouTube?
from?
Is there a YouTube?
Binghamton.
Oh, that's good to have you down. You have a really nice. I don't want to stream this. There's a over in New York. You have a place where the
The little snake.
yes, yeah, like perennial flame, I think they call it. There's a like and light gas comes out of like a waterfall
Is
area.
that right?
Yes,
Yeah, I didn't know that.
yeah, it's
Well,
over
at
in
some point, but we're not here all the
the
time.
southeastern part. Yeah, over there.
Yeah?
Yeah, a little, you can light the flame up, like an internal flame. Yeah.
Now, you don't think they use the salt springs here for like the medicinal springs? They was just for
That-
salt.
there was
They
no way.
didn't bathe in these things for special.
There was no record of that. I mean, one of the problems is that it doesn't produce much water, and so it wasn't. It's not like a what you might have like an artesian.
It's not like a
saline
hot springs.
hot spring. It's definitely not hot, so you don't have that there. Like,
Okay.
so you don't have it like a.
So
out
this
west.
was just interested in salt.
Yeah, there was a salt seep, and again, the Native Americans used it for trading, enough to dry and use. They also probably used it to salt their food. And the thing was that the Native Americans weren't telling them where this was.
Oh, okay.
Because
So
they
you said it's what, 300 feet?
300 feet deep. Now it might be caved in by now, but that was done around I think the mid 1800s.
Hand dug? Or not drilled?
No, it could be drilled. What they were doing with drilling then was basically just hammering on stuff. You'd basically have a sharp stick and put a little metal point on it and go like this, and then it gets dull, take it out, and
Do it again.
do it again, and then when you advance 10 feet, you get another piece of casing and put on, and then you push the casing down.